everyone. I'm going to talk about modeling of fracture using physics-informed deep learning. Fracture is important design consideration in engineering, and these two examples at the top would confirm that. It's also useful in the study of fracture of rocks and in biomechanics in fracture of bones. One of the prominent ways of studying fracture and modeling fracture is phase-field brittle fracture modeling. And the idea is that originally fracture is a surface of discontinuity, and within this one regularizes this surface of discontinuity. So we end up with a phase field which when equals 1 that represents a fracture, and then it decays slowly away from fracture with certain length scale, which is a numerical parameter, or it could be problem dependent. Now, the important part is that this process is governed by an energy functional, which has first part elastic strain energy and another part associated with fracture. And also, importantly, this formulation essentially governs all the various types of fracture processes that are important in engineering, and we classify them separately as sort of different fracture problems, so to say. And that's why this is something that could be useful. And we want to be able to use machine learning, physics-informed deep learning, to be able to model this. Now, first challenge, of course, is that to be able to show that physics-informed neural networks can actually learn all the different kind of fracture processes that happen before we can actually utilize this for any further applications. And the main challenge essentially comes from the fact that even though we have regularization, we still have sharp interfaces present in the model. Sorry, not sharp interfaces, but sharply varying fields present in the model. Now, the energy functional that we have is a non-convex energy functional. And so to minimize it and get the solution, we directly use deep Ritz method, where loss function directly E equals the energy functional in the variational formulation. And then by minimizing it, we can reach the stable local minimum solutions. So now, as I said, that even though we have regularization, we still have sharply varying fields present in the solution. And part of the reason is because the length scale associated with this regularization are still very small, up to 2 order, 3 order magnitude smaller than the size of the domain. And that brings challenges in learning the solution. And we sort of rationalize it in terms of representation of the energy surface in the space of neural network parameterization, neural network parameters. And that helps us identify the sort of neural network that would be able to do the problem, which essentially is that it should accurately represent the energy barriers and the energy minima associated with the solution. And then we need an optimizer which respects these energy barriers and takes us to the correct solution. And with this, then we were able to show that we can capture all the different fracture processes using deep learning approach. So on the left top corner, we have crack nucleation in a L-shaped panel. Here on the right at the top, the red line is actually initial crack, and then crack propagates from there because of application of some loading. And then under certain condition, this crack basically can bifurcate, which is shown on the bottom right corner. And on the bottom right corner, we have crack coalescence in some sample which has pre-existing notches present. We also look at the accuracy of solution in terms of the energies associated with these different solutions. And we find that neural network is reasonably well able to model, basically learn the solutions. Also, we look at the basically the robustness of solution, and the standard deviation shows that basically the approach is robust in the sense of initialization of network with different initializers, and we find that we are able to learn the solution. So this brings me to the close. Thank you, and look forward to discussions with you.
Thank you, Manav.